we want to talk about confidence intervals for proportions, right? We were talking about means where you're trying to approximate mu. Now we're looking at a sample proportion, p hat, to estimate rho, the population proportion. Clearly, we don't know rho, because otherwise, why would we bother estimating it, okay? So there's not a sigma that we're worried about knowing or not knowing. We're just looking for rho, and we don't even have a rho to start with, okay? So we're trying to estimate rho, and this is actually the only confidence interval formula on your formula sheet. It says statistic plus or minus critical value times standard error of the statistic, okay? So in this case, our statistic is p hat, because that's what we got. We got p hat. That's our predictor. We always, even though we don't actually know rho, we always get to use z star with proportions. There's no t distribution for proportions. It's always z with proportions, which is nice, okay? Because you don't have to worry about degrees of freedom and all that mess. Then times the standard error of the statistic, and this is my square root of pq over n, but we don't know p, so we use p hat and q hat over n. That's my standard error. And so we'll do this plus or minus z star times that. All right, that's going to be our formula that we get to use. Same old conditions. It needs to be a simple random sample. Normality, we're not worried about central limit theorem, robustness, all that stuff, because we know that a binomial distribution is going to be relatively normal when NP and NQ are 10 or more, okay? And independence, we need, most of the time we're sampling without replacement, so we need a population 10 times as large. That's what we call the 10% rule, okay? So let's do a quick example. So rating dorm food. Tanya wants to estimate what proportion of the students in her dormitory like dorm food, okay? So we're trying to calculate what is rho here, and rho is the true proportion of students in dorm who like dorm food. Okay? The assumptions, random. Simple random sample, check. Independent, 50 of the 175 students living in the dormitory. That's less than 10%. Uh-oh. Or greater than 10%, excuse me. Okay? The population is not going to be 10 times greater than the sample. So, not met. What do? Proceed with caution. Okay? What caution are we going to take? Nothing. We're just going to say proceed with caution, because when they tell you to find a interval, you get to the interval whether or not you've met the conditions, okay? So proceed with caution, all right? And then normal. Well, it says that she thinks that 14, or no. So 14, find that it's good, which means that 36, okay? NP equals 14, NQ equals 36, both greater than or equal to 10. So we're good right there, okay? So name the interval. So this is a one proportion Z interval, okay? One proportion Z interval. And how do we calculate it? Well, we want to take our P hat plus or minus our Z star times the square root of P hat Q hat over N. All right. You can do this by hand, or you can do it on your calculator, and I'll show you that real quick. So stat tests. We're going to do a one prop Z interval, and it's not on this list. We got to go a little bit lower. One prop Z interval is A. My X number of successes was 14. My number of trials was 50. That's all it asks for. Because guess what? It gets the P hat from that. 14 out of 50 is going to be 0.28. It does everything that it needs from that. and it calculates your interval 0.15555 and 0.404. So I'll call it 0.16 to 0.40. Okay. And then we can draw a conclusion. Our conclusion is we are 95% confident that the true portion of students in her dorm who like dorm food is between 0.16 and 0.40. Done. Okay. So relatively easy. Same ideas that we had from earlier. You get a p-hat. You can always use z-star. You never need a t-star. And square root of pq over n is the standard deviation of our sampling distribution. So good luck and farewell.